All right. Hello. Okay. So we're moving on. So this is probably the last class for the second module. Okay. So in the last lecture we talked about three different ways of doing feeding. Basically, you have some data. In this case, we are dealing with maybe some H points and want to feed a line. Right? That's a canonical example. And this class will be talking about how you can use this feeding to align models. Okay. All right. So just a quick recap. Like if I have the simplest one is that I have a bunch of data points and I want to feed a line that pass through, like basically explain these data points. The simplest approach is to assume that you have an objective function that says that, okay, I have a line equation that's y equal to mx plus b, and I want to find what m and b is. And the way we do this is that for every m and b, I have a say objective function that's EE that tell us how well how well this line passed through the data. Okay, and the way we do this is that I can take measure the vertical arrow for any x I and measure the predicted value and the actual value. Okay, so this is the things. And as we talked about last time, you have an objective function. It's a function of some two parameters, m and b. The way you solve this is to take the derivative over m and b and set them to 0. Then you can solve this. Okay. So this is how we do this. You take the function and take the gradient and set them to 0, and this will advise that this is the least square solution for to solve this. Okay. But we talk about this, it's not great because it's not able to represent vertical line, right? In the vertical line, your m, the slope is infinite. And that you couldn't like describe any images that has vertical lines. All right, so this is bad. So instead of measuring, we changed the objective function from measuring the point to line, vertical distance from point to line. We measure the distance from point to the line, the closest distance from point to the line. Okay, so this is called total least square. So we can, again, you can represent the line equation as ax plus by plus c. That's any line equation. And you measure the distance between the point to the line with this. That's your e. And again, you can set the parameter, set the computer gradient with respect to that parameter and set them to 0. That's how you can find the minimum. Okay. And we now find this minimum c is this guy. Is minus a times the mean of the x and minus b times the mean of y. Then if you plug this in, this will give you this linear system equations that has this form. Okay. And if you just look at this form, you'll find that it's kind of the minimizer seems to be trivial, right? So trivial means that if you just set a and b, that's your parameter to 0, then the whole thing is minimized, right? It's 0. Because you have a quadratic function, it must be the smallest number is 0, right? Smallest value is 0, okay? But that's not a right solution because you have a constraint on a and b. A and b in this case, because a and b represent the direction of the line, and therefore a squared plus b squared must be equal to 1, okay? And we talk about this problem looks like this. You have to minimize this subject to some constraint. Okay. So this will give you the solution of this is that you conduct eigen analysis, eigen decomposition of this A transpose A, and you pick the smallest, pick the eigenvector corresponding to the smallest eigenvalue. Okay, that's how you can solve this. All right. So you have so this is great. You have the method for solving least square that measure the vertical arrow, and this total least square for measuring this closest distance. But the problem of this is that it's not robust to outliers. So we need something that's robust to outliers, right? So this is bring us to the half transform idea, right? The half transform basically says that if I want to detect a model, what I need to do is that my model has some parameters. In this case, the model parameters is the line parameter. It could be the slope and the intercept, or it could be the rho and theta, right? It's by specifying the rho and theta, I specify a line in the image space. Right? The half transform idea is that for any observation in the image, I cast votes on all the possible lines that pass through that point. Okay. So, and then because you have multiple observation in the image space, then you'll be able to cast votes in the solution space or the parameter space in the and with that you can figure out what exactly because the right solution will accumulate the most number of votes. And that's how you can get the right solution come out of this. Okay, so this is great because it's robust to outliers. Even though you have some random points in your image, you can still detect that model because the outlier will not be able to accumulate enough votes. Okay. Right, but the problem of this is that you have, imagine you have, your model has more parameters, then you will need to maintain that memory of all the parameters, right? So you need to, for example, you have a three-dimensional, you need to maintain like a grid of three-dimensional structure, right? And if you have each grid has 100, then you have 100 times 100 times 100, right? So it's going to be very quickly go out of hand. Right? So that's the problem of half transform. And therefore, we try to have another method that's called RenStack. Like at the end of lectures, the RenStack idea is super simple. If I want to detect a line, a bunch of different through a bunch of different observation, and this observation is very noisy, how do I find the line? Okay, the way we do this is to randomly sample a hypothesis. Right? In this hypothesis, it's kind of the guess that any 2 points, I will form a line. Like that's my model hypothesis. Okay, I want to check is this a good line or not, right? And the way we check whether it is a good line or not is to draw a boundary between this line and see how many of the data point agree with this hypothesis. Okay, so in this case, I can count how many of them. It's like a 6 that pass through this line. Okay. The reason why you need to have a boundary is because that all those points are noisy and they do not, even if you have a virtual line here, you couldn't really have a line that lie exactly on that line. Okay, so you need to have some slack to count that those points, some of the points are the inlier or not. Okay. So you can see that this is not really a good guess because it's not many of the other points agree with this guy. So you do this again, like in this case, you will find more inliers. Then outside of that range, those red points are the so-called outliers. So they are not really, maybe there are some incorrect matches or something like that. Okay. So that's good. That's the RenStack. All right, so this is a quick overview of the 4 main methods we talk about. All right. Question about these 4 methods. Right? Optimization-based methods, least square, total least square, and half transform and RenStack. Right? And then the point is that you're probably not like actually implementing this stuff yourself, but you want to know when you will use what. Right? So, for example, some problems, for example, you want to see if there's no outliers, then you may want to use this optimization-based method because you can get really accurate results. If you want to detect multiple, you want to use half transform. If your model has multiple parameters that higher degrees of freedom, you may want to use RenStack. Okay, so all these methods has some pros and cons that you want to be aware of. Okay, questions? Good. All right. So this is something that I glanced over last time. Basically, like how do you know how many of the samples you need? right? So this depends on a couple of things. It depends on this number of n, the number of sample you need, depends on the number of sample you need to determine a model, right? If I have a line, then that's 2 points, right? I need two samples. If I have I want to detect a circle, then it's 3 points, right? So 3 points will fully determine a circle, right? If I have some other things, I may have more number of parameters. Okay, that's the number of points needed, and you have some distance threshold that you need to determine. Okay, how sensitive your range should be to determine what something is inlier or outlier. Okay, and with that you can compute this from these equations. You can compute like how many of the outliers, how much outlier you can tolerate. Okay, so imagine that here, this is how you can read this graph. If I only detect a line, that's 2 points determining a hypothesis, then depending on the outliers, percentage of outliers, these are the number of samples that I will need to draw, like every pair of samples I need to draw to ensure that at least one of the pairs is inlier within certain probability, like 99% of the probability. Okay, does it make sense? Imagine that you have a 50% of outliers. Basically, I have a bunch of points, and some of 50% of the points lies on the line, and 50% of the points are just randomly scattered in space. And in that case, I need to sample 17 trials, 70 pairs of points to ensure that at least I have 99% of the time that one of the pairs has passed through that where both points are inliers. Okay, and there's the equation that you can do that. I can all right. So you can see that if your model gets more complicated, like later on we could have model that has A parameters, right? So in the third module, we will talk about when you try to estimate a homography, that is estimate how one image is related to each other, that has A parameters. And in that case, you'll need, like if you have a lot of outliers, you need to sample a lot, right? To make sure that like the probability of sampling A points, that is that all A points are inliers, is going to be you need a lot of samples. Okay, does it make sense so far? Okay, so RenSec robust with outliers. It's applicable to larger number of objective functions. It's great. And yeah, the problem is that you need to sample more. Okay, and it's not as good as fitting a multiple fit, right? You can do that, but it's not that efficient. All right, so which operators I should use? Like we talked about this before. Okay, if you know that everything is inliers, like you know absolutely right that this is there's no outliers, then you probably want to use least square approach, like either least square or total least square. If there's outlier, you want to use either like robust fitting or RenSec. If you want to detect multiple things, you want to use Hopf transform. Okay. All right. So another thing that's very common, not entirely in computer vision community, but it happen a lot in the medical domain and the graphics domain, is that you have points, point sets, right? I have a 3D point set here, 3D point set here. And how do I align them? Okay. So in this case, the Hopf transform, because you don't have the correspondence, the Hopf transform is not applicable. So you need to do something that if I know the correspondence and I can shift that, I can align them, right? But the initial correspondence is not available. And therefore, I need to do something else. So this is some application. For example, let's say you do a CT scan of your like a health check checkup, like you do a CT scan, and maybe 6 months later, you do another CT scan, right? You need to somehow align these two CT scans so that the doctor can see what changed, right? So this is kind of alignment problem. And if you imagine that you have some 3D reconstruction software, you run some 3D reconstruction on one building, and you have another drone that captures another thing. So how do you align them so that you have a single 3D reconstruction? Okay, so all these problems can be solved using a very simple algorithm called iterative closest points. Okay, so here's how it works. So of course, like imagine that you have two CT scans, like it's just some 3D point cloud. And the way you do this is that you need to first initialize the transformation, right? Like maybe first initialize the center and the scale of these points. And then for each point, you want to be able to find the correspondence of the other set, right? For each point in one set one, you want to find the correspondence in the point in set two, right? So assign the correspondence. And the way you can assign the correspondence is going to be noisy, but that's okay. You can find that through the nearest neighbor, right? Basically, if you align these 2 point sets, and then for each point, you find the closest point. And then after step 2, you have the correspondence. Once you have the correspondence, you can solve the transformation. You can figure out what the transformation is by solving this square, right? And once you have this, you can apply the transformation to the 1 point set to another set, okay? And just repeat, right? Now you have something that's closer, and then you can repeat this process until convergence, right? So let me just show you the example. It looks like this. So imagine I have 2 partial scans. Initially, it's far away, but what you do is that you iteratively try to find a transformation that can align one set to another set, okay? So this is very useful when you don't have the correspondence that's given by the feature matching. Okay, for example, you have a point, you don't really have a description about that point, but you only have 2 sets. But this is the way you can help you align it. Okay, so let's see one example about solving a very simple translation problem and through fitting. Okay. So imagine that, and let's see what type of method we can use. All right, so imagine I have two images. Okay, imagine that the point of trying to solve the transformation is that I can use this to detect. I detect an object, detect a face, detect a car in the image. Okay, so obviously it has a lot of applications. So let's say in this case, I have image A and image B. Okay, I have image A and image B. And then I have, let's assume that you want to know what is the offset, like the X, Y, delta X and delta Y, or TX, TY here, so that these TX, TY are related to this one, okay? Right, so basically XB, the image, the second image is the translated version of the first image, okay? All right, so how do you solve this? If I already give you all the correspondence, right? XA1 match to XB1, XA2 match to XB2. All right, but of course, they are somewhat noisy, okay? They may be noisy. So how do I solve? Like, let's assume first, like all the points are accurate. All the points are there's no outliers. How do I do this? Any idea? Yes. Subtract the numbers. Can you say that again? Sorry. Yeah, they're all the same dimension. So I just give you, let's say in this case, I have 5 points, right? I have 5 points in the image 1, which basically for each point you have X and Y, right? And then another 5 points in image B, okay? And I tell you that point 1 and point 2 are point 1 in A and point 1 in B is matching, okay? But I need to find the unknown txty. What kind of method will you try? If I just subtract that, you can subtract if you just take one point, corresponding matching point in image A and image B, you can subtract this and you can get an estimate. But the problem is that you only have this coming from just one correspondence. But now I have 5 correspondence. What will we do? Okay, if I don't have the outliers, how do I fit this? I'm trying to apply the fitting to solve this computer vision problem. Any idea? Anyone? So we just talked about this, right? So yes. Yeah, if it is no least square, we can just solve for it. Okay? Yeah, that's right. So it looks like this. The solution looks like this, right? So whenever I try to solve this square, I have this kind of steps, right? So first one is write down objective function. The objective function is make sure that this guy minus this guy is as small as possible, right? Basically make sure it's small as possible. And then I can derive the solution, like compute the derivative, and then either solve for Ax equal B or solve pseudo inverse or eigenvalue decomposition, right? So what is the linear system equation for this one? It will look like this, right? So pretty much all the computer vision problems we have encountered so far can be solved by something like this, right? I have unknown. Right? Anytime I have an unknown, the tx and ty, I just put them in a column vector, and I just look at the equation I was given, and I represent that equation with this guy, right? So essentially, I have tx, ty in the column vector that's unknown. Then I have something that's a that's known. And in this case, it's just 1, 0, 1, like 1, 0, 0, 1 for each pair of correspondence. And then on the right hand side, I have the difference between the correspondence. Okay, so I can then solve this square using by looking at this. Like this is the A, and Ax equals B, and as soon as I write that representation, and I can solve this with this square. Okay. Okay, so other setting. Let's say I have this some correspondence. Some correspondence is correct, but some correspondence is not correct. Like I have some outliers, right? How should I do this? How do I do this? And I only in this case I know that it is only one object. Any idea? Yes. Rensec. Okay. Yeah. So, and in this case, what will be the how many sample do I need to form a hypothesis? The hypothesis here is the txty. Any idea? Like previously, I have a line. I need to sample two points to form a line. That's my model hypothesis. But what is the model hypothesis here? Any idea? How many samples do I need to get? And here the sample is in terms of correspondence, right? Each pair of data is a correspondence. Okay, this is this point matches that point. But how many correspondence I need to get in order to compute a txty? Any idea? A correspondence means that I have a point xy in this position in the image A and another xy in image B. Do I need 2 or 3 or 1 pair so that I can come up with a hypothesis that's what's the translation? Yes.
In theory, many of
Why 2? 2 unknowns. Let's see. Indeed, we have 2 unknowns. But every time I sample a pair of correspondence. I already know that this point did match to this point, and this point, this A1 match to where's A1, A2 match to A2. It's just that they may be wrong. Minimum 1, yes, yes. We don't know what is outlier or not, so we have to make a guess, right? What I'm asking is how many correspondence pair I need to get in order to determine a model. In this case, the model is TXTY. So it only need 1 pair, right? If I give you a point, these 2 points are correspondence, then you automatically know the offsets, right? That's the TXTY. So I only need one sample to get that. Okay? So 1 pair of correspondence is my, I can, with 1 pair of correspondence, I can form a hypothesis. Okay? So now how do I apply this RANSAC, right? So in this case, it looks like this. So first you sample a set of matching pair, right? That's the correspondence. Like this point match to that point. You don't know whether that they are the beauty of this is that you don't know if they are outlier or inlier. You don't care. You just try and then see once you find a pair, you can find, okay, is this going to be a good hypothesis or not? You just try to score that hypothesis, okay? And in this case, basically, imagine this, right? X1, let's say X1 and B1, this vector is this vector, right? It's shifting this vector. And how do you see whether how many inliers are there? Maybe there's in total 5 correspondence. What you do is that you apply that TXTY, that's your hypothesis, and to move all the points in image A and shift that points to the second image. And then you check whether whether that shift can predict the correspondence well, right? Some of them will have a very large arrow that's going to be outliers. Some of them are not, okay? So imagine if at this point, this A4 and B4, this is the wrong correspondence, right? And if you shift all these data into that positions, the correspondence doesn't match up, and then you'll get a lot of outliers, okay? And this is how you can use this. If you sample enough pairs, you will be able to figure out what exactly what are the inliers, what are the outliers. Okay? Yes.
do the shift you check match. You have to allow some error.
Yeah. You can think about yeah, because the points, even though they're close, they are not going to be exact. You cannot use the equal sign in Python. You have to see, okay, if there's 2 points, it may be the distance, you clear the distance if they are sufficiently small. You have some like an arrow that you can describe.
Is there like a confirmation? It's sufficiently small or
right. So that will depend on your understanding of the nodes, right? Maybe but typical way, it also depends on resolution, right? If you have a smaller resolution image, then you probably will have a larger tolerance. If you have high resolution, or if you have a high resolution image, maybe have larger tolerance. If you have the same very precise, then you can say, okay, I count the pairs is inliers only when these 2 points, the offset point and correspondence is more than 1 pixel. Then it's correspond. That you declare that is an inlier. Okay, so you have some threshold that is a hyperparameters that depends on different applications. Okay, but this is the way to solve for some alignment problem without without knowing what is inlier or outlier. And this is super important. It's maybe not just in computer vision. For any problems you ever encounter, you want your algorithm to be robust, right? So this is kind of probably the go-to tricks for you to build something that's robust to outliers. Okay. All right. So how about other scenarios? Like I have kind of correspondence. I do have correspondence, but it's a many-to-many mapping. Okay. So I have this, like you can see the big cats match to this big cat and this guy match to this one. All the correspondence. How should I solve this? I couldn't use RenSec anymore. Any idea? We sort of there's only one left, right? So, all right. So it's going to be Hopf transform, all right? So the way we do this is that in Hopf transform space, our solution space here is just TXTY. So it's very easy. You just have all this TXTY. And for every correspondence pair, you cast a vote in the TXTY space. Right, and then when you cast the vote, it's only 1 point, right? So what you do is that you cast this, initialize those pair, you cast a vote, and then you figure out what is the once you cast a vote, and for all the points, later on what you'll find is that you will probably find like there are 2 dominant shifts that they all agree with each other, right? For example, this guy. The shift between A1 and B1 agree with A3 and B3, right? They also have the same shift, which means that their votes will accumulate in the solution space. Okay, and same thing here, like A5 and A6, the shift is like this directions, and shift is this directions, and they will accumulate the same votes, right? So in the solution space, you will find that there are 2 clusters. Right, and that way you can detect multiple detections. Okay. All right. So one last thing is that what if you have like unknown correspondence? Right. In this case, we use the iterative closest points. Right. So you don't have correspondence. Previous method is that if you know the correspondence, then you can use this square to solve the transformation. That's the TXTY. But in this case, we don't have a correspondence, and therefore, what we do is to first kind of guess a correspondence. And the way you guess the correspondence is to use the closest nearest neighbor. Okay, and you need to find a correspondence for each point and compute transformation and move the points using transformation, and then iterate. So you can see that the 2-point sets can then get pulled together and gradually converge. Okay? Yes?
How to define nearest?
The nearest neighbor is that, okay, all these points, they are X and Y, right? Another point set is also X and Y. Right? Each point is described by 2 numbers. And the nearest neighbor is that for every point in X, every point is described by X and Y in image 1. And then you just look for all the points in the image 2, and each point has its own X and Y values. You just find that maybe the Euclidean distance.
So there are like 2 individual sets of points.
Yeah. So this has a lot of application, right? You have 2-point sets, but you don't know how to match them. But you know that if you know the matching, you can solve the alignment problem. But in this case, you don't know the initial matching, so you need to guess it. Okay.
So it's each point in just one.
Yeah, for every point you find the nearest neighbor in the second image, then you now you have a initial estimations of the correspondence, and then you can shift this. Okay, so this is something that you play with in the homework 3. Okay, so sorry that there's a lot of this is just I just want to put everything in one slide. There's lots of fitting algorithm, right? So but the important thing, like we go through the toy example is to go through that. Okay, how will you choose from depending on which one which algorithms are there? Okay, how do you choose them? Okay, so next we want to talk about the these are the algorithms, these are the kind of toolbox that you'll use, and depending on what scenarios, you will know when to use what toolbox. And this is the concept of fitting. Okay, I have a model, and from data, I want to fit the model. All right, so now I want to talk about the alignment problem. The alignment basically says that I have some model, and I want to the model itself is a transformation model. Okay, we'll show you what that transformation looks like. So in fitting, so in the previous lecture, we talked about this, right? I have a model, maybe the model is a line, it's a curve, it's a sphere, or some other parametric models. The model, the problem of fitting is that I want to find the model such that the difference between the model and the prediction of the data is as small as possible. Okay. So, and what is the alignment here? Alignment is similar, very similar. The alignment says the following. So if I have a data points, maybe some feature points from image 1, and I also have image 2, but the image 2 undergoes some kind of like transformation. Okay. The goal is to really find that transformation is, right? So it's basically I can solve alignment. Like how do I align these 2 point sets? By solving this. Okay, I want to find the t such that if I transform the t from ti, that's the i's point in the first image, this guy after transform, it will be very close to the corresponding point, right? Does this make sense? Okay, so this is the concept of relating to alignment and fitting, right? So we have the tool about fitting. Now that the alignment is basically saying that instead of fitting a line to a bunch of points, we are fitting a transformation. Okay, a transform. I want to find what transformation that give me this that can explain this correspondence. Okay, so some applications you do every time you pull out your form and try to capture a panorama, it's solving alignment problem. Okay, why? Because you need to make sure that you understand, because you take one image and take multiple images, right? How do you know they are related? How are they related to each other, right? You need to solve for the correspondence and solve the alignment so that they can be kind of put together, right? They could become a panorama, right? So you want to get something like this, you can generate a clear panorama. Okay. Some other application of alignment is that I have some model, maybe have some model like city, and I take a picture. How do I know where that thing is? It's basically you have a data set of the location. You want to be able to match, right? You want to be able to align how that thing is related in the image. Right? That's an alignment problem. Okay. So in reconstruction also is very like basically you need to understand you have a model and images, and how is this related to each other? Okay. All right, and so this is a very common alignment problems. So here, this is using SIT to align the 2 images. Can anyone tell me how are these 2 images aligned with each other? Any idea where the feature correspondence is? These are they have some correspondence. So let's see how your vision versus the kind of these feature detections. They look very different, right? But they have some correspondence. How do you find the correspondence? Yes. The flow on the second image. Oh, this one. Match where? Oh, the top left of the first image. Okay, so I can visualize this by showing the SIP features. Okay, so this look like this. So the way you can align these two images, like in the Mars rover, they have this functionality, right? So they will take multiple images because your camera does not have a very wide field of view. Okay, even if you have a wide field of view camera now, you cannot ship it to Mars. Okay, so whatever they have there, they must work there, and you cannot really control this because any signal you send to Mars, you need like 11 minutes to get there. Okay, even travel the speed of light, you still couldn't really control it. So everything needs to be automatic. So this is how they, the NASA Mars rover are operating on Mars. They are able to capture the panorama of the scene so that they can navigate, they can send a stitched panorama back to Earth. Okay, and this is how they do it, right? So they need to find the matchings and then align them so that they can create a panorama. Okay. All right. So the general problem of alignment is basically the following. So I want to find the parameters of a model, right? The alignment, some parameter models, and those parameters are usually global, means that one image and another image. Okay, so there's just only one transformation that can describe the whole image. Okay, and the challenge is that you need to handle noise, you need to handle the outliers, and sometimes many to one. Okay, so let's talk about the basic one. So here's the so-called the transformation, what the class of transformation. The transformation you can think about is essentially a coordinate changing machine. Okay, I have an XY coordinate, and I want to the coordinate change to X prime, Y prime. Okay, so P to transform to P prime. Okay, and when we say the transformation is global, what we mean is that it applies to any points, right? There's only one transformation that describes the transform from one image to another. Okay. And one type of transformation we particularly like is linear transformation, because the linear transformation can express the transformation with just a few numbers. And these numbers, the transformation can be described as linear matrix vector multiplication. Okay. So these are common transformation. They look like this, right? So imagine that you have an image. You can translate, you can shift the image, translate or rotate, or you can change your aspect ratio and affine and perspective. Okay, you have multiple different ways of doing transformation. All right. So now what we want to do is to understand these are very intuitive, but we want to understand the math behind it. Okay. So how do what kind of transformation model that allow us to achieve these type of transformation? Okay. And this is essentially, you can do this with just simple matrix vector multiplication. Okay. And once you have that matrix vector multiplication, now the problem will become, I give you a 2-point sets, and like basically the C feature detections, and you match the correspondence. Then how do I find the transformation? Okay. All right. So first of all, scaling is very simple. You can scale this image, like you have an image of a house, and then you can scale it up to 2 times. You can also do non-uniform scaling. You can just scratch one axis, and all this operation can be simply described by these linear system equations, right? So x prime, that's a new coordinate for the x location, is ax, and y prime is by. So, and then you just express the coordinate, this transformation in the linear transformation formula, then you get something like this, right? It's very compact representation, right? So x prime, y prime equal to a scaling matrix that just scale along x, scale y unit, a unit, and scale y is b unit. Okay? Make sense? So this is very super simple. Okay? So this is just a scaling, and you can change like either you want to, you can have a non-uniform scaling and so on. Okay. How about rotation? Right, if I x, y and rotate along the origin, so you get something like this. Okay. So you have an x, y, and you rotate theta from x, y to x prime, y prime. Oh, sorry, x prime, y prime, and the transformation here is a little bit complex, right? So you have the x, you have this theta, and the transformation is basically the x prime here equals to x times cosine theta minus y times cosine theta, right? And y prime here is x sine theta plus y cosine theta. Okay, so there's some proof that this is true. If you can express this with the polar coordinates, like you express the x and y equal to the sine phi, cosine phi, and x is r, radius r times cosine phi, and y is r times sine phi. Okay, and then you can express this, right? X prime, y prime is this guy, and then you kind of just do some high school math, then you will arrive at the solution. Okay. Okay, so you can see that this guy is sort of complicated, right? Because it's because theta and the cosine theta, a cosine function is a nonlinear function, right? It's a nonlinear function with respect to theta, right? So this is kind of complicated, but the interesting part is that the relationship between y prime, x prime, y prime, that's a new coordinate, and the old coordinate xy, they are still linear with respect to the x and y. Okay, which means that you can write this as a matrix form like this. Okay, so this is what I said. Even though the sine and cosine, they are nonlinear function with respect to theta, but from the perspective of input coordinate xy and output coordinate x prime, y prime, they are still linear because x prime is a linear combination, linear transformation of x and y prime is a linear transformation of x and y as well. Okay. All right. So, and here's a trick. This is a question for you. Like, if I have a rotation of xy and rotated theta to get x prime, y prime, what is the inverse transformation of this? If I have a r rotation that transform x1, what is r inverse? Can I get r inverse quickly? Yes. Can you say that again? Sorry. One side to negative to the on side to another side. This guy to this one. Okay. And what is this operation called? If I take a matrix and I don't change the diagonal part, and the off diagonal I swap them. What is the name for this operation? Transpose. Okay. This makes sense. Does that refresh your the memory? Right. So you have a function. You have a matrix, and then if you do this, you can express the inverse as a transpose. By the way, why you rotate the inverse transformation of the rotating by theta is just the transpose? Why is that? Why do you know that the inverse rotation is just the minus move to here? Any idea? Yes. Inverse of the matrix. Yeah, that's true. But I'm asking why that's the case. Yes. Yeah, so I have a rotation R that this matrix R represent the rotation by theta. But now I have inverse rotation, inverse transformation of this R. And that inverse rotation is basically rotated by minus theta. Okay, yes. Sorry, I couldn't get it. So here, I think the key here is that because an inverse transformation of a rotation by theta is just rotation by minus theta, right? So it's kind of inverse, right? If I rotated theta and then rotated back minus theta, then it's at the same location, okay? So that's the identity. So basically, if this is rotating by theta, and the inverse transformation is just replace the theta with minus theta. Okay, that's R inverse. Okay, and then why this guy is just shifting the sign is because the cosine is an even function, right? Cosine theta and cosine minus theta is the same. It's just cosine theta. And what is the this sine wave sine function? It's an R function. Okay, so you can think about this, right? So the sine theta starting from 0, and it's symmetry, it's anti-symmetry along the 0. Okay, so if you have a sine minus theta, it's minus sine theta, and therefore you have this guy become minus and this guy becomes sine. Okay, and that's the kind of the reason why you have this transpose. Okay. This is super convenient, and especially in computer graphics. Anytime you want to do the rotation, especially 3D rotation, you don't need to really compute that like inverse of that 2D matrix. If the transformation R is a rotation matrix, you just need to compute the rotation transpose. Then you get the transformation. Okay. Okay, so you have these transformations, but then we talk about scaling and rotations. Can anyone tell me, like, how do I represent a translation? Right? It seems very simple, right? If let's say x1 is equal to x plus 1. Can I implement that with a 2x2 matrix? Is there a way to do this? It's not a linear transformation in this case. So that is kind of, this is kind of annoying, right? Because like even with simple translation, I cannot represent that simple translation as a linear transformation of the x and y. Okay? But there's a trick. The trick is the following. Okay, so look at the basic transformations. So here we have this this I1, this scaling and shear. That's just shearing x and y, and rotate, and you can have translate. And the translation, the trick is that I just add a 1 and like just expand the 2-dimensional vector into a 3-dimensional vector by artificially adding a 1 at the end. And now in that space, there's a name for that space. It's called homogeneous coordinate. In that space, I will be able to represent the translation, okay, by just putting xt, xty here. So now you can see that the new coordinate is a linear transformation of this xy1. Okay, you can represent the translation this way. Okay, so now any of the transformation can be described by something is called affine transformation that incorporate all the possible translation, scaling, rotation, and so on. Okay, so these are the basic 2D transformations. So let's see some applications. So and later on we will talk about all these other things. Okay, so this transformation can help you align the image. For example, one plane to another plane. You can use to do this align the images so that you can stitch them into a panorama. And because the transformation can be aligned through these will describe any transformation between one plane to another plane. So there's some application like this. Okay, let me show you.
Use office lens. Just frame.
So, but this is the kind of neat application of this transformation. So every time, for example, you have some document you want to scan, and the way you do this is try to capture this from the top, right? But usually it's hard, you have shadows. So what you could do is that you capture the things from an angle, but because you know that they are planar, you can apply a transformation from that location up to a frontal parallel, okay? So you would have application like this. Let's see.
Use office lens. Just frame your shot from any angle and snap a picture. Office lens automatically crops, straightens, sharpens, and cleans up whiteboard images. Save the image to OneNote or OneDrive and get it from any of your devices. Or share the image in an email. Do you ever worry about misplacing important documents? Switch to document mode and Office Lens will trim and color the image perfectly.
Okay, so it's very simple application of this transformation. Once you figured out the boundary of these documents, once you can see that how they do it. Okay, you can see that they have the whiteboards here, but you don't want to capture the image itself, right? The capture image itself, the content is slanted, right? So once you can apply the transformation to unwarp that, you can compensate that. Then you get something like that.
Office Lens automatic.
Okay, so it's I think it's very neat. It's very, very simple applications. All right, so so this is just a summary of what the kind of basic 2D transformation from translation, only two parameters, txty, and rigid transformation. It has txty and the rotations, and the similarity transformation. It's just a name, like you have a rotation, scaling, and translation. Okay, and you can use this to do a variety of applications, like the corrections. You can do this video stabilization. You have a shaky video, and you can compensate that, like create a smooth version of the video, and so on. Okay. All right, so now if I want to match this object instance, how do I do this? Okay, so the key idea here is that I have a correspondence matrix, right? And then I can solve for that parameters, right? Using this alignment concept. All right, so first of all, let's see what the key point matching algorithm looks like. Again, we have two images. In the left-hand side, you have the ground. Maybe you have the reference image, and you want to find what's the transform, how the second image is related to the first image. That's what you want to achieve. Okay. The way you do this is that you first independently for each image, you find the interesting points. Okay. Basically the idea is that you run the difference of Gaussian to figure out what are the kind of stable regions, what are the regions, the XY location and the scaling that has a large response. Then you figure out that the corresponding regions, right? For each regions, you have this normalized patches, right? This normalized patch, and you can extract some features, okay? Extract some features, let's say we talked about last time, you have the C features, and then you try to figure out the matches. Okay. So once you have this matrix, you can do the matching, right? Once you have the matching, then each point matches, you can vote for the you can vote for the, like, what is the scale difference and the rotation difference. And then you can basically find the votes. Okay. So that's basically how you can find the objects. I want to probably focus on this part. Okay. So now the key difference between fitting and alignment is that alignment is essentially fitting, but trying to fit the transformation. Okay. So now the problem here is the following. So I have a collection of metrics. Okay. So I give you two images. You detect feature points for image 1, detect feature points for image 2, and you do feature matching for these points. You get a correspondence. Now for each correspondence pairs, you have a relationship, okay, like this. And here the unknowns is this matrix, 2x2 matrix, that is the combination of scaling and shear and rotation, right? You don't know what the scaling is, you don't know the shear, you don't know the rotation. So you describe this 2x2 matrix plus the T1, T2. That's an unknown translation, okay? So you have this guy, okay? So you know, like a compact way to describe this is that you have a xi plot equal to nxi plus t, okay? So our goal of formulate the alignment problem, a fitting problem, is to find the phi. I want to find the m so that the nxi minus t is as similar as txi as possible. It's very intuitive, right? I have a collection of points, I have correspondence. I want to find what is the transformation that is n and t, such that if I transform those points xi to xi, that should be very close to xy plot. Okay, so I want to find the transformation. Okay, so throughout the class, we only typically, like in all the different problems, we only have one tool. Okay, so now I have some unknowns. How do I solve this? Any idea? How do I solve this? Yes. These squares, yes, but how do I formulate the problem? Right? What's the first step? Okay. What will be the first step if you want to approach this problem? Yes. Identify your unknowns, and then essentially you move these unknowns into a column vector. Okay. So this is the setup, right? So I have linear system equations, and then I basically vectorize my unknowns, right? So here you can see that my unknown is not just tx, ty, right? My unknown is m1, m2, m3, m4, and t1, t2, right? These are my unknowns, and I put the known values into some missing entries here, and the right-hand side is some output like this, okay? And then for each pair correspondence, right? I have x prime, y prime matched to xy. Each pair of correspondence will give me two equations, okay? So it will look like this, right? It will look like this. You have this matrix. You can see that what I'm doing here is to just express the same equation, but express that same equation into the form that I can solve with d squared, okay? Like throughout the class, we have been seeing this over and over again, right? So the same techniques, okay? All right, so now the question is, did you have a linear system of 6 unknowns? So, And we know each match pairs, you can see that each match pair XY and each match pair of XY and X pawn, Y pawn will give me two equations. So how many pair correspondence do I need to solve this? Okay, I have six unknown numbers, and each pair of each correspondence give me two equations. How many equations are there? How many pairs do I need? Yes, idea? 3. Yeah. So I only need 3 equations, right? So three pairs. So eventually pictures look like this. From the 3 correspondence, if I have 3 points and I know how to move these 3 points, I give you any type of affine transformation. Okay. And this is how you can use this to recognize objects, right? So if I have an object here, I basically for each object, I find the correspondence in the image. Then what I do is that randomly sample 3 pairs of images, and then I can start to figure out what is the relative position and scale from one reference object to the target object. Okay. Okay. And this is basically how like any type of recognition, instant recognition system. It has been pretty successful in early days. I think right now you can also download there's some robot dogs that can recognize some specific instance. If you have some instructions, they can recognize these cars, because these cars they have a mental models there, and they will have a vision system on board. They will be able to do, okay, if you recognize this car, they will do certain things. Okay, so the application is driven by this instant recognition. They have some specific patterns, and that will be able to once they recognize something, they can perform specific tasks. Okay. All right. So let's see. Okay, I will probably leave out the large scale retrieval. All right, so basically that's kind of how we can we talk about the feature matchings, feature extraction, feature matchings, and then how you could do the fitting, apply the fitting to alignment. So this is a basic idea of module 2, like basically kind of how do you extract features and do the matchings. And we're going to use this module 2. In module 3, we're going to use that to solve for 3D visions. Okay, basically from multiple images, how do I extract the 3-dimensional structure from 2D images? And that involves the understanding of the camera and understanding of these feature matchings. Okay. All right, so I'll stop here and then have a great spring break. Thanks.